Welcome back. Our subject for this session is the basic diagnostic tools. Any trade or profession evolves tools of the trade. These are numerous, but they follow the Pareto Principle. A few basic tools are enough to do most of the work. The tools for diagnosis are also numerous. They also follow the Pareto Principle. A few diagnostic tools are enough to diagnose most problems. During this session, we will review these basic diagnostic tools. First, let's look at data sheets, since everything starts with data on symptoms. Data are collected on a wide variety of data sheets, diaries, logs, journals, and so on. A primitive example is the tally sheet used during a roll call. As the votes are called out, the ayes and noes are recorded as tallies. Every fifth tally is entered diagonally to simplify computing the totals. It looks like the noes will win this one. Some data sheets are designed to permit recording of multiple variables. A common example is the matrix of defect types and workers. This data sheet is a tally of the errors made by those insurance policy writers. What we saw previously was the totals derived from this tally sheet. The widest use for tally sheets is to record data on inspection and test. Let's demonstrate by use of the pinball machine. The technical name is QUINCUNX. Despite the exotic name, the QUINCUNX responds to reasonable requests. QUINCUNX, please appear. Thank you. Believe it or not, this is a manufacturing process. The raw material is those beads at the top. The process has 11 variables. There are 10 rows of pins. There's also a row of the tops of the dividers between channels. Each variable can cause a bead to bounce to the right or the left. The final destination is the resultant of the cumulative effect of all those 11 variables. The scale can be any quality characteristic, amperes, grams, millimeters. As the beads drop down, data recording is automatic. The device is also a means for tallying data. Now let's make some product. First, let's set up the process. We will aim the funnel opening at 13 on the scale of measurement. Here we go. First unit, second, third, fourth. Notice the variations in the product units. The setting remains at 13, but the units are not alike. Let's dump these units into finished goods inventory, and then make more and more and more. Look at the accumulation building up down below. We're building up a frequency distribution. This is the second of the basic diagnostic tools on our list. QUINCUNX, thank you for your assistance. Now let's look at an actual case. Here are data on electrical resistance of 100 coils. The tallies show how many coils there were at each value of resistance. The tallies also show the shape of the distribution. That helps to visualize the data collectively. The frequency distribution exhibits two main features. First, a central tendency. The data are bunched around some central line. We can quantify central tendency. There are several measures. The most useful is the average, also called the mean. The average is simply the sum of all measurements on individual units divided by the number of units. In mathematical symbols, the average is written as follows. In this formula, X with a bar over it means average. This capital Greek sigma means the sum of. Any X is an observed value. And N is simply the number of observations or units. A second feature of the frequency distribution is the scatter or dispersion. There are several measures of dispersion. The most important is the standard deviation. The standard deviation is defined by a formula. We won't get into this, but later we will look at some uses of the computed value of standard deviation. Another symbol for standard deviation is the Greek letter sigma, lowercase sigma. Next, the frequency histogram. It is really a block diagram with heights equal to frequencies. Here is how it looks for that case of the electrical resistance of coils. This histogram is graphic, easy to interpret as to central tendency and as to dispersion. Let's look at some examples of use of histograms to judge the ability of the process to hold tolerances. This is the ideal situation. This process is clearly able to hold a tolerance and is actually doing so. The center of the histogram is at the midpoint of the tolerance limits. This process is also able to hold a tolerance, but is not actually doing so. The reason is the process has been set off-center. That results in much oversized product. This is similar to the previous case. The process is able to hold a tolerance, but an off-centering results in much undersized product. In this case, part of the histogram is missing due to sorting of the product to remove the defects. This process is well-centered, yet it makes many defects, both oversize and undersize. The reason is that the inherent dispersion of the process is too wide for these tolerances. Here again, we have a high percent of defectives, both oversize and undersize. This is due to a mixture of product from two different off-centerings of the same capable process. In those histograms, it was easy to judge by eye whether the process could hold tolerances. We can go further. We can compute process capability in numerical form. The simplest cases are those in which the frequency distribution has the familiar bell-shaped curve called the normal curve. Here's how it looks. For any normal curve, the zone between plus and minus sigma contains about 68% of all the data. The zone between plus and minus 2 sigma contains about 95% of all the data. The zone between plus and minus 3 sigma contains 99.73% of all the data. This 99.73% is so close to 100% that some practitioners call plus and minus 3 sigma process capability. Having standardized on process capability equals plus and minus 3 sigma, The practitioners also standardize on the relationship of process capability to tolerance limits. Engineers in the automobile industry commonly require that process capability, that is plus and minus 3 sigma, be no greater than 3/4 of the distance between bilateral, that is plus and minus, tolerances. Next, the Pareto analysis. This tool is used to divide multiple phenomena as between the vital few and the trivial many. Here are some of the examples we saw. The paper mill made 53 types of paper. Waste in the form of broke was $556,000. But 6 of the 53 types accounted for 80% of the broke. The job shop had numerous processes, but 6 of them accounted for 69% of the rejections. In the weaving department, there were 323 yards of defective cloth, but 3 of the 15 weavers had made 74% of the defective cloth. We can dramatize the Pareto analysis by the use of graphs. The horizontal scale is persons, weavers. The vertical scale is percent defective. The columns show the performance of each weaver. The contrasts are obvious. The cumulative line shows how 3 weavers account for 74% of the imperfect cloth. Next, the orderly arrangement of theories. There are 2 forms. First, the tabular form. The table shows theories, sub-theories, sub-sub-theories in their interrelationship. Secondly, the graphic form. The fishbone diagram shows the same data as the tabular form, the same hierarchy of theories, but with better eye appeal. Next, process dissection. In many processes, the product progresses sequentially through a series of operations. Here's the material source. Here's a series of operations, steps in the process. At the end is a test station. We call this process dissection. We saw an example in the case of the gouged gun barrels. There, the gouges showed up at the end of a sequence of 3 operations: drill, re-drill, and ream. To dissect the process required 2 added gauging heads for the air gauge. Then we discovered that the first operation was guilty. A second form of dissection is by streams. Processes, the product emerges as multiple streams. For such processes, the need is to dissect based on the stream of origin. Our model shows streams converging to create a mixture. Dissection requires going back to the stream of origin. An example was the carpet yarn study. The 88 yarns had their origin in 88 parallel ribbons cut from a continuous sheet of woolen fibers. During normal processing, these ribbons lost their traceability. Dissection by stream required special methods to be invented to trace identity back the stream of origin. A second example was the case of the polishing operation. The product exhibited many patterns of unpolish. The study team separated the product into 138 different streams, each traceable to the fixture of origin. That confirmed the theory of worn fixtures. For purposes of diagnosis, workers are also streams. To test theories which are worker-oriented, we must establish dissection or traceability to worker of origin. In the piston ring foundry, the diagnosis required setting up elaborate, unprecedented traceability, including by worker. One finding was that the melter Knight's castings resulted in less scrap than those made by any other melter. The matrix of worker versus defect type is also a form of dissection by worker. An example was the case of the insurance policy writers. That was a matrix with defect types in one direction and workers in the other. It resulted in useful disclosures. Another matrix form combines dissection by workers with test of time-to-time consistency. The matrix for the gun assembly case shows the workers in one direction and time, month to month, in the other direction. It conclusively proved that some workers consistently had 10 times as many defects as others. A further diagnostic tool is time-to-time analysis. It involves tracing defects back to the time of occurrence. The gun assembly matrix included departmental totals, month by month. The wide variation was a useful input to the overall solution. Our earliest example was study of several hours of production of shafts for the watches. That study showed a time-to-time variation. The diameters grew progressively larger due to wear of the cutting tools. We also saw an example of cyclical change in the carpet yarns. The chart shows the weight of consecutive equal lengths of yarn, but the machine speed was constant. Hence, the chart also shows time-to-time variation in yarn weight. The duration of each cycle also became evident. This helped to identify the cause of excess variation. Cumulative failure analysis is a further form of time-to-time diagnosis. Such analysis is possible only if the product units are date-coded so as to provide traceability. When cumulative failure data are plotted by calendar time, the result is like the case of the consumer apparel. One curve shows cumulative percent returns for product made in December. The other curve is for a new design made in February 14 months later. We can simplify the comparison by changing the horizontal scale from calendar months to number of months following the date of manufacture. Now the chart looks like this. This chart makes it easy to draw important conclusions. For the old design, the returns rate is constant. The cumulative curve does not level off. The new design has a dramatically higher returns rate than the old. And these cumulative curves are sensitive detectors of change. If this chart had been in existence at the time, the managers would have learned within 3 months that the new model was headed for serious trouble. Similar time-oriented diagnosis can be applied to the large units of product. Now the evidence of failures comes from the cost of service calls, not from return of the products. Our case example involved a product line of heavy equipments which had been plagued with high costs in field service calls. When the data on these costs were put into cumulative form, the cumulative curves for successive model years looked like this. The chart shows clearly the growth of a serious problem and its ultimate decline. The time scale of this rise and fall was matched against the history of major events in the product line. And there emerged a synchronism which settled a long-standing dispute about responsibility for the high costs. Next, the WEIBULL analysis. The horizontal scale is amount of use in any unit of measure, time in hours, kilometers of travel, cycles of operation. The vertical scale is cumulative percent failures and is a probability scale. Suppose now we run a life test on 10 units of product. The first failure occurs at 34 hours. So we plot a point at the intersection of 34 hours and 10% failures. A second unit fails at 58 hours. we plot that on the 20% line, since 20% have failed cumulatively. We continue charting until all have failed. A curve through the points will approximate a straight line. From the curve, some useful estimates can be made. For example, what will be the service call rate during the warranty period? What will be the need for spare parts? An actual case was the comparison of the fatigue endurance of bearings made from two different materials. The two WEIBULL curves are helpful for quantifying the economics of field performance and thereby for finding the optimal overall cost. A second application was the comparison of the failure rates of brake systems under accelerated tests by the manufacturer versus use by clients. Because the manufacturer's tests lead clients' use by 1 or 2 years, these WEIBULL curves help to provide early warning of what will be future field performance. Next, concentration diagrams. We saw some examples. One was leaks in rubber gloves. This evidence of concentration helped to unify the thinking of the managers so they could direct their efforts toward a solution. Another example was chipped enamel on household appliances. The concentration in the corners matched one theory and led to a solution. A famous example in epidemiology was Dr. John Snow's study during the London cholera epidemic of 1848. One diagnostic tool used during that study was a street map showing the addresses of those who had died of cholera. The center of the concentration was the Broad Street pump, which made the water suspect. Next, correlation studies. A simple case was the ranking analysis of the torque tubes. The defect was dynamic unbalance. Of the 7 worst product types, every one had been swedged. Of the 7 best types, none had been swedged. That left no doubt of the influence of the swedging operation. A more elaborate case was a study of the pits on the piston rings. Their data sheets were used to record information on process variables. Correlation of time to pour metal with percent pit scrap provided support to the theory of the importance of time. Finally, there's a wide range of experimental designs. The simplest is a split lot. Half of a material batch is processed by method A, the other half by method B. If material is also to become a variable under study, we can set up a 2-by-2 experiment. Analysis of the horizontal and vertical sums tells us a good deal about the relative effects of these variables and their interactions. If we add a third variable, we need a more complex design. We saw an example in the die casting case which used a 3-by-3 Latin square design. Here, the combination of high mold temperature and high melt temperature gave the least porosity. Now let's look back at the high points of this session. Diagnostic tools are numerous, but a relative few tools are enough to solve most projects. The most widely used tools include data sheets, frequency distributions, average and standard deviation, frequency histograms, process capability analysis, Pareto analysis, orderly arrangement of theories, process dissection, time-to-time analysis, cumulative failure analysis, WEIBULL analysis, concentration diagrams, correlation studies, experimental designs. Between now and the next session, look over the list of diagnostic tools as summarized above. To what extent have these tools been used in the company? What is your conclusion? As to your current project, look to see whether these tools are applicable for aiding the diagnosis. Also, read the workbook notes for session 12. Good luck.